In this discussion video, we will do another example where we find where a function has its critical numbers and its local extreme points and its inflection points. So the function is x squared e to the negative x. This problem is coming from part C of this worksheet problem, number 3 from worksheet 10, where we want to find the critical numbers, determine which of them are local maxes and local mins, and find any inflection points. So at first I want to give you 12 minutes to try this problem. There are going to be a lot of steps here because we'll need to do the first derivative, the second derivative, and make a sign chart for both. So pause it in 4, 3, 2, 1. Pause it for 12 minutes and really try this question on your own. Alrighty, so hopefully you did that. Hopefully you paused it for 12 minutes and tried this. If not, definitely do that. Okay, let's talk about it together now. So let's first find the critical numbers and local extrema. Critical numbers and local extrema. So that just means the local extreme points. So to do that, I'll need to take the derivative. And for this derivative, I need product rule. So that'll give me the first function times the derivative of the second, which will require chain rule. So I'll get e to the stuff times the derivative of the stuff. The derivative of the exponent is -1. And then plus the second function, e to the negative x times the derivative of the first, which is 2x. And now I want to simplify this because I need to figure out when is 0, when is undefined. So let's factor, and I can factor out an e to the negative x. I can also take out an x, that's common to both of these. And doing that, we'll be left with a negative x from the first term, and then a +2 from the second term. All right, so our derivative equals 0. Okay, and it might be helpful to bring the e to the negative x to the denominator. I get x times negative x plus 2 over e to the x now. All right, so our derivative, let me scooch this down. Our derivative equals 0 when? Because I have this fraction, the numerator needs to be 0. And that happens when x is 0 or 2. That's why it's helpful to have it factored. And our derivative would be undefined when the bottom is undefined. But, sorry, when the bottom is 0. And that never is going to happen. This derivative is never undefined, since the denominator e to the x, this never equals 0. No matter what power I plug in for the x, e to any power is always positive. It'll never be 0. Okay, so we are ready for our sign chart. So let's make a number line. I'm going to plot any point that makes the derivative either be 0 or be undefined on the number line, regardless of whether it's in the domain of the original function. Okay, so we just have 0 and 2. And now I'm going to put all the factors of my function as rows here. So I'll have x, negative x plus 2, e to the x. And once I have those, I could write down the sign of my derivative and then what that tells me about the original function f of x. All right, let's separate out some rows. And then I'll separate out some columns, a 0 and a 2. Okay, and at 0, with the factor x, that's positive when x is bigger than 0, and it's negative when x is less than 0. With the negative x plus 2, this is positive when x is smaller than 2. So it's going to be positive over here, and it's going to be negative when x is larger than 2. We already said e to the x is always positive. We could also visualize that by drawing the graph of e to the x. Remember, the graph of e to the x has this shape. And that graph always has positive outputs, positive y values. Okay, so if we combine these signs, a negative times a positive, that is a negative. Similarly, this last column is going to be negative, and this middle column, when we multiply those signs, gives us a positive. Okay, so when our derivative is positive, the original function is increasing. It's going to be rising. And when the derivative is negative, the original function is decreasing. It's going to be going down. So here as well, it is decreasing. Okay, so we are ready to write down our critical numbers. So critical numbers, these are numbers that make the derivative either be equal to 0 or be undefined, that are in the domain of the original function. Okay, so far we have x equals 0 and 2 as values that make the derivative 0. I got to be careful to check, are they in the domain of the original function? And with this original function, well, the domain of this is actually all real numbers. So 0 and 2 are definitely both going to be in the domain. These are both in the domain of f. Okay, so these are critical numbers. If one of these wasn't in the domain of f, it would not be a critical number. It would still go on this number line because it would still be a place where my derivative might change sign, but it wouldn't be a critical number. Okay, but that doesn't happen here. Alrighty, so let's classify these now. So at x equals 0, our function changes from decreasing to increasing, so we'll have a local min at x equals 0. And this is since, I'll give a reason why, since our original function f changes from decreasing to increasing at x equals 0. And the other part I need is this has to be a number where my function is continuous. And my function, x squared e to the negative x, this is going to be continuous everywhere. Okay, so x equals 0, this will be a local min. Alrighty, and then at x equals 2, our function changes from increasing to decreasing. That gives me a local max. That gives us a local max at x equals 2. And that's since f changes from increasing to decreasing. And because our function is continuous at 2. That's also important. So let me write that in parentheses here. And because f is continuous at 0. The continuity part is really important, because if my function wasn't continuous at 0, I could have hypothetically had a scenario where it was decreasing to the left of it, maybe because of a vertical asymptote, and then increasing to the right. But I wouldn't have had a local min, because there's no point on the graph where x is 0. My function is not continuous there. So that's why the continuity part is important. All right, so next let's find the inflection points. So let's find inflection points. So for this, we're going to need to take the second derivative. So let's recall that our first derivative in factored form was x times 2 minus x times e to the negative x. And to make it a little bit easier to do the derivative of this, I'm going to multiply the x times 2 minus x first. That'll give me 2x minus x squared times e to the negative x, because now I just have two functions multiplying each other. So this is a little bit easier when I do product rule. All right, so thus, this implies when I do the second derivative and I do some product rule, I get the first function, 2x minus x squared times the derivative of the second with chain rule, that's e to the negative x times the derivative of the exponent, which is negative 1. So I'll just write that negative in front. And then plus the second function, e to the negative x, times the derivative of the first, which is 2 minus 2x. And now let's factor. So I can take out an e to the negative x, that's common to both of these, and that'll leave me with, let's see, a minus in front of 2x minus x squared. If I distribute that negative to both of these terms, I'll get negative 2x plus x squared. And then for the next term, I'll have plus 2 minus 2x. Okay, so we get e to the negative x times, we'll have x squared minus 4x plus 2. And let me bring the e to the negative x to the denominator. And this expression on the top won't simplify. I could try to factor it, it just doesn't factor though. I get x squared minus 4x plus 2. And hopefully maybe you got to the point where you saw that when you tried this in that 12-minute pause at the start, when you took the second derivative hopefully, and then tried to factor it and set it equal to 0 and figure out when it's undefined. Okay, so now I need to figure out when is this second derivative equal to 0 and when is it undefined. So our second derivative is going to be 0 when the numerator equals 0, x squared minus 4x plus 2. So I need to figure out when this quadratic equals 0. So I can use quadratic formula. We'll get x equals negative b, which is 4 plus or minus the square root of b squared, negative 4 squared minus 4ac. So 1 times 2, all over 2a, so over 2 times 1. So this becomes 4 plus or minus square root of 8 over 2. And simplifying this root, we get 4 plus or minus, this becomes 2 root 2, because I can take a 4 out of the root, and that becomes a 2 when I take it out. And then divided by 2, And then I can split this up as 4 over 2 plus or minus 2 root 2 over 2. And that'll give me 2 plus or minus root 2. Okay, so that's when my second derivative equals 0. When is this undefined? Well, our second derivative is never undefined. Never undefined, because that denominator never is 0. Since e to the x is never equal to 0. So one of the things that I'm going to need to do with my sign chart is figure out when is x squared minus 4x plus 2, when is it positive and when is it negative. And because my cup points, my tick mark points are not as nice this time, I have these roots, it helps to visualize this function. So the graph of y equals x squared minus 4x plus 2, because this is a quadratic, this graph is going to be a parabola, and the leading coefficient, the coefficient in front of the x squared is positive, so it's going to be an upward-facing parabola. Okay, and it turns out that the parabola looks like this, where both of the x-intercepts are positive. So the bigger of the two x-intercepts is 2 plus root 2. The smaller of the two is 2 minus root 2. And I know both of them are positive because I know the smaller one is positive because 2 is bigger than square root of 2. 2 is bigger than square root of 2. That's what makes this positive. That's how I know these x-intercepts are going to be positive. Okay, so I can use this graph to help me when I make my sign chart. Okay, so let's make our number line, and I got to plot these points that made my second derivative either equal 0 or undefined on it. So I got to do 2 minus root 2 and 2 plus root 2. And then I have to write all the factors of my second derivative as rows. So the numerator I had x squared minus 4x plus 2. The denominator was e to the x. Then I can combine those and write the second derivative and then write a row for f of x, the original function. All right, so let's separate out some rows and separate out some columns. Let's start off with the e to the x because I think that's easier. That's always going to be positive. E to the x is always positive, right? This one we've seen before. The numerator, this is where the graph helps me. The numerator is negative, it has a negative output, negative y values, between these two x-intercepts. So in this middle region, this is going to have negative outputs. And the outsides, to the left and to the right of these intercepts, to the left of 2 minus root 2, I have positive outputs, and to the right of 2 plus root 2, I have positive outputs. Okay, and then positive divided by positive is positive. Similarly here it's positive. And then a negative divided by positive is negative. So when the second derivative is negative, f is concave down. And when it's positive, f is concave up. So it's going to be concave up here. So the question wanted the inflection points now. And it didn't just want the x values, it wanted the whole point. Okay, and at 2 minus root 2 and 2 plus root 2, the concavity switches, and at both of these, the function, the original function, is continuous at them. Okay, so both of these are going to be inflection points. So the first one, its x-coordinate is 2 minus root 2, and the y-coordinate is what I get if I plug this into the original function. So remember, the original function was x squared e to the negative x. So if I plug this into that, I get 2 minus root 2 quantity squared times e to the negative 2 minus root 2. Okay, and similarly for the other one, the x-coordinate is 2 plus root 2, and the y value, when I plug that into my function, is 2 plus root 2 squared times e to the negative parentheses 2 plus root 2. Okay, so these are the inflection points since f changes concavity. Let me just write concave, and is continuous. The original function is continuous at these x values. So for practice now, I want to graph this function. Technically, we've reached the end of our previous example, but let's graph it for practice. So to do this, we need to combine the sign charts. Combine the sign charts of the first derivative and the second derivative. Okay, so I'm going to make a number line. And I'm going to put a tick mark at every point that had a tick mark at in either the first derivative sign chart or the second derivative sign chart. So from the first derivative sign chart, we had tick marks at 0 and 2. Okay, so I'll put one at 0, one at 2. And in the second derivative sign chart, we had tick marks at 2 minus root 2, which I know is positive, it's greater than 0, and at 2 plus root 2. Okay, so 2 minus root 2 is going to be somewhere here, 2 minus root 2. It's definitely less than 2, because I'm doing 2 minus some positive number, and we already showed this was greater than 0. And then 2 plus root 2 is definitely going to be bigger than 2. 2 plus root 2. Okay, and now I need to keep track of my derivative, my second derivative, and the shape of the original function f. Okay, so I'm going to make some rows and some columns. In our first derivative, you know what? At this point, let me do a quick pause. Let me have you pause it for 3 minutes and see if you can finish this one off, filling out the sign chart and then drawing the graph. 4, 3, 2, 1. Pause it for 3 minutes to see if you can finish it. Alrighty, so hopefully you did that. Let's talk about it together. So for the first derivative, it's positive between 0 and 2, and negative everywhere else. So my first derivative is positive between 0 and 2, and negative elsewhere. So negative elsewhere. And now for the second derivative is negative between 2 minus root 2 and 2 plus root 2. It's negative between them, but positive elsewhere. So this is negative between 2 minus root 2 and 2 plus root 2, but positive elsewhere. Okay, so based off of that, I'm going to do the first column slowly, and the remainder more quickly. F prime being negative means my function is decreasing. And the second derivative being positive means my function is concave up. So decreasing concave up looks like this. The next one is increasing concave up. Then I have increasing concave down. Then I have decreasing concave down. And then I have decreasing concave up. Okay, so those are what the pieces are going to be. Okay, so now let's try to put this together. So I'm going to draw the graph of y equals x squared e to the negative x. And I'm going to try to line my axes up. So I'm going to try to line my x-axis up with these tick mark points. So at 0, at 2 minus root 2, at 2, and at 2 plus root 2. And one thing that'll be helpful to do is if I just plug 0 into this, if x is 0, the y value is going to be 0. So one point on this graph is going to be 0, 0. So 0, 0 is a point on that graph. And looking at my sign chart to the left of 0, my graph is going to curve like this. So it's going to curve like that. Between 0 and 2 minus root 2, it'll increase and be concave up, so something like this. And then at 2 minus root 2, it switches, it keeps increasing, but it's concave down. So it switches concavity. We have an inflection point there. And now from 2 to 2 plus root 2, it's going to decrease. It's going to have this shape. Okay, and then from 2 plus root 2 onwards, it's going to switch to being concave up. And it'll turn out that it looks like this. It turns out it has a horizontal asymptote here at 0. We technically don't know how to show that yet, but let me just give you a little preview. So it turns out, so we already said that it goes through this point 0, 0. If we're really rigorous with this, it turns out the only x-intercept of this graph is 0, 0. The only y-intercept of this graph is also 0, 0 if we go through the process of finding it out. And it also turns out, to find the horizontal asymptotes, I got to take the limit as x goes to infinity and as x goes to negative infinity. And the limit as x goes to infinity of x squared e to the negative x, this ends up being 0. And we actually show this. We can show this with something called L'Hopital's rule. L'Hopital's rule, and that we'll cover in our next section, 4.4. And that's why I knew that as x gets really, really big, these y values are getting close to 0, because I have this horizontal asymptote at y equals 0. And it also turns out that on the flip side, as x goes to negative infinity of x squared e to the negative x, this one I don't need any special rule for. I can just sort of plug in. We'll get negative infinity squared, and then times e to the negative infinity, which is positive infinity. And negative infinity squared is positive infinity. E to the infinity is also infinity. And infinity times infinity is infinity. So for our horizontal asymptotes, there's only one. And the one horizontal asymptote only occurs in the sort of x going to infinity direction. So y equals 0.